What specific problem does the WAN model aim to solve in the context of video generation, and how does it compare to existing methods?
The WAN model aims to address the significant performance gap between open-source and closed-source video generation models, particularly in terms of suboptimal performance, limited capabilities, and insufficient efficiency. Existing methods, primarily focused on general text-to-video (T2V) tasks, often fail to meet the diverse demands of video creation, which require more specialized functionalities. WAN introduces a novel architecture that combines diffusion transformers with flow matching, enhancing computational efficiency and text controllability, while achieving robust performance across various dimensions, such as motion quality and stylistic diversity. Additionally, WAN offers a scalable 1.3b model that runs efficiently on consumer-grade GPUs, significantly improving accessibility compared to larger models that require extensive computational resources. This positions WAN as a competitive alternative to both commercial and other open-source models, demonstrating superior performance in multiple benchmarks.
How does the proposed WAN model work? Could you illustrate its architecture and training process step by step?
The proposed WAN model operates through a carefully designed architecture that integrates a variational autoencoder, VAE, a diffusion transformer, and a text encoder, specifically UMT5, to facilitate high-quality video generation. The architecture begins with the WAN VAE, which encodes input videos from pixel space into a latent space, compressing the spatiotemporal dimensions while maintaining essential features. This latent representation is then fed into the diffusion transformer, which consists of a patchifying module, transformer blocks, and an unpatchifying module, where cross-attention mechanisms embed text conditions to ensure the model adheres to user instructions. The training process is divided into two main phases, pre-training and post-training. In the pre-training phase, the model undergoes a staged joint training approach, starting with low-resolution images and gradually incorporating higher-resolution video data, allowing for effective cross-modal semantic alignment. The training objective utilizes flow matching to model a unified denoising diffusion process, optimizing the model to predict velocities between latent representations. In the post-training phase, the model is fine-tuned on high-quality video datasets to enhance visual fidelity and motion dynamics, ensuring robust performance across various video generation tasks. This comprehensive architecture and training regimen enable WAN to achieve state-of-the-art results in video generation, including capabilities for image-to-video generation and real-time video synthesis.
Can you provide a specific example of how the WAN model generates a video from a text prompt? Walk through the main steps of the generation process, including any input transformations that occur.
The WAN model generates a video from a text prompt through a structured process that involves several key steps. Initially, the input text prompt is encoded using the UMT5 text encoder, which transforms the text into a sequence of embeddings that capture its semantic meaning. Next, the model utilizes the WAN VAE to compress the video input into a latent space, where the first frame of the video is concatenated with 0 filled frames to create a context for the video generation. This context, along with the noise latent and a binary mask indicating which frames to generate, is then passed through the diffusion transformer, DIT of the WAN model. The DIT employs a cross-attention mechanism to integrate the text embeddings with the video latent features, allowing the model to generate coherent video frames that align with the provided text prompt. Finally, the generated frames are decoded back into video format, resulting in a complete video that reflects the input text.
What are the main advantages of using the WAN model over traditional video generation methods and existing open-source models?
The WAN model presents several key advantages over traditional video generation methods and existing open-source models. Firstly, it achieves superior performance through its innovative architecture, which combines diffusion transformers with flow matching, allowing for enhanced motion quality, visual fidelity, and stylistic diversity in generated videos. Secondly, WAN is designed for efficiency, offering a 1.3B model that requires only 8/19G of VRAM, making it accessible for use on consumer-grade GPUs while outperforming many larger open-source models. Additionally, WAN's extensive training on a dataset comprising billions of images and videos enables it to excel in various downstream tasks, including image-to-video generation and real-time video generation, which are often challenging for traditional methods. Furthermore, the model's comprehensive design includes a full spatio-temporal attention mechanism and optimized computational strategies, ensuring robust performance across multiple dimensions, such as instruction adherence and camera control. Lastly, WAN's open-source release of its training processes and model components empowers the community to develop specialized foundational video models, fostering innovation and collaboration in the field.
How was the WAN model validated and what metrics were used to measure its performance? Discuss the datasets and benchmarks employed in the evaluation.
The WAN model was validated through extensive experimentation across various tasks, utilizing large-scale datasets comprising billions of images and videos, amounting to trillions of tokens. The evaluation focused on 10 key visual dimensions in video generation, including action, camera angle, camera motion, object category, object color, object counting, OCR, scene, style, and event. For performance measurement, the model's outputs were compared against those generated by Google Gemini 1.5 Pro, calculating F1 metrics for each dimension based on a sample of 1,000 videos and their corresponding captions. Additionally, the model's performance was benchmarked against state-of-the-art techniques in tasks such as image-to-video generation, video continuation, and first-last frame transformation, demonstrating superior results in visual quality, motion quality, and matching. The datasets used for evaluation included curated collections from both internal sources and publicly available data, ensuring a diverse and high-quality training foundation.
What limitations did the authors identify in the WAN model, particularly in terms of its applicability in real-world scenarios or performance constraints?
The authors identified several limitations in the WAN model that affect its applicability in real-world scenarios. Firstly, despite the impressive performance of the model, there remains a notable performance gap between open-source models like WAN and the latest closed-source models, particularly in terms of suboptimal performance and limited capabilities for diverse video creation tasks. Additionally, while the 1.3B model enhances inference efficiency and can run on consumer-grade GPUs, it still requires significant computational resources, which may hinder accessibility for creative teams with limited resources. Furthermore, the model's reliance on extensive training data and complex architectures can lead to inefficiencies in real-time applications, particularly in generating high-quality videos quickly. Lastly, the authors noted that the model struggles with generating human vocal sounds, which limits its effectiveness in scenarios requiring synchronized audio, such as speech or vocal elements in videos.